Sunken naval fleets. The mystery of impossible hull fractures. Look closely at this steel. This was once the armored hull of a 20,000-ton dreadnought. Reinforced plating. Riveted seams. Engineered to survive artillery barrages and open ocean warfare. But now? The metal curls inward. Jagged. Twisted. As if something grabbed the steel and folded it from the outside in. Ballistics experts say this fracture pattern shouldn't exist. Pressure physics says it shouldn't look like this. So what actually happened down there? Recent high-definition ROV dives have captured 8K imagery of scuttled naval fleets resting thousands of meters below the surface. These vessels were intentionally sunk. Some were war casualties. Others were decommissioned and sent to the deep. But in multiple wreck sites across different oceans, investigators noticed something strange. Localized hull tears. Not blast holes. Not corrosion. Not uniform collapse. Instead, sharp, inward curling serrations in the steel plating. Sections appear peeled back in concentrated zones, almost like pressure was applied in a tight, focused impact point. If this were a torpedo strike, you would expect outward fragmentation, an explosion pushing steel away from the blast center. But these fractures curve inward, as if the force came from outside and compressed inward before tearing. Modern torpedoes use high-explosive warheads designed to create shockwaves and bubble pulses beneath hulls. The result? Upward structural failure. Hull breakage along stress lines. Massive outward rupture. But these dreadnought hulls don't show that signature. There's no symmetrical blast radius. No secondary fragmentation patterns. No burn residue consistent with explosive detonation. Even more puzzling, some affected vessels were scuttled decades after active combat service. No recorded attacks. No classified engagement reports. Which eliminates traditional weapon explanations. At extreme depths, hydrostatic pressure is crushing. Steel eventually buckles. But pressure collapse failures follow predictable physics. The hull implodes uniformly once structural limits are exceeded. You see smooth inward deformation across broad surfaces. You don't see narrow, jagged tearing. And you certainly don't see concentrated serrations in isolated patches. Yet that's exactly what ROV footage shows. These are not global collapses. They are localized structural events. Structural engineers analyzing the footage suggest something unusual. The fractures resemble kinetic shear, force applied rapidly, laterally, and in a confined area. Not an explosion. Not gradual compression. But a sudden transfer of energy focused at specific impact points. Think of bending a thick metal sheet with a hydraulic press. The steel doesn't shatter evenly. It folds, then tears along stress paths. Some sections of these wrecks look exactly like that. The question becomes, what could generate that kind of focused force thousands of meters underwater? Naval records show that deep ocean hydrophone arrays occasionally capture unexplained acoustic events. Short bursts. Low-frequency pulses. High-energy signatures that don't match seismic tremors or submarine propulsion. Most are logged, categorized as unknown, and archived. But when analysts mapped certain acoustic anomalies against wreck coordinates, patterns began to emerge. In a few cases, unexplained acoustic spikes were recorded in the same general regions where unusual hull damage later appeared. Correlation does not equal causation. But the overlap is enough to raise questions. Before jumping to conclusions, investigators examine natural possibilities. Subsea landslides can generate massive lateral forces. Turbidity currents can move debris at highway speeds. Underwater volcanic activity can create shock events. But again, those forces affect wide areas. The hull fractures in question appear selective, concentrated, targeted in small zones rather than distributed across entire structures. That's what makes them so difficult to explain. Here's what the evidence supports. The fractures are real. They are inward curling and jagged. They contradict typical explosive damage patterns. They do not match standard pressure collapse physics. They appear localized rather than catastrophic. Beyond that, speculation begins. And responsible investigation stops short of fantasy. Because the deep ocean is not just mysterious. It is violent, dynamic, unpredictable. The ocean floor holds war relics frozen in darkness. Steel giants that once ruled the surface now rest in silent trenches. Some of them bear scars we don't fully understand. Not impossible, but unexplained. And until deep-sea monitoring becomes as advanced as surface surveillance, certain forces, natural or otherwise, will remain hidden beneath layers of pressure and time. The mystery isn't proof of something supernatural. It's proof that we still know very little about what truly happens in the deepest parts of our planet. And sometimes, the steel tells a story long before we understand the language. Please like, subscribe and follow for more.